All right, welcome to the unit on Introduction to Probability. I want to first talk about independence and mutually exclusive. And we took a little bit of these notes in class, but I want to make sure we have these down. I can just clarify anything with this first. So this symbol here, the upside down U, just stands for the probability of A and B happening. This over here, the B with the line and the A, stands for probability of B given A has occurred. And why it's important to notice is this right here is a general form. If you want to know the probability of two events happening, you can just multiply those events together. If these events are independent, so if A has nothing to do with B, so if A's event does not affect the outcome of B, we call that independence. Okay, if these two things are independent, in which case the probability of A and B is just the probability of A times the probability of B. If you have a situation where they're mutually exclusive, what that means is if A occurs, B cannot occur. And that means that the probability of these two events are zero. So again, if they're mutually exclusive, what it means is that if A has occurred, then B cannot occur. So if you look down at these problems, which you did in class, if you select a marble, put it back in, and shake up the bag and select another, the probability of selecting a blue 5 out of 20 times 5 out of 20, because you put them back in the bag. So you have 5 out of 20 the first time, 5 out of 20 the second time. If you don't put them back in the bag, then they're no longer independent. So 5 out of 20, and then you have 4 left out of 19. So you notice the probability will change just a little bit. Now, for the sake of all these notes in the work, you do not have to multiply these out. If you want to leave them like this, this shows your understanding. I really don't care about your understanding of being able to multiply fractions. That's a different course. This one is showing me what these events and outcomes are. Now, as far as the other formulas are concerned, this is OR. So this stands here for probability of A or B. If you're talking A can happen or B can happen, we're looking at addition. But with a Venn diagram situation, and really what this comes down to is if you have A here and you have B here, if you add all of A and all of B, what you also done is added this section twice, because this is in both A and B. That's why you have to take away one of the probabilities of A's and B's. So that's where this formula comes from. This formula here, okay, is a generic formula for A given B. I'm going to tell you right now, we're not going to be using this formula much at all. So you really don't need to worry about that formula. That idea of A given B you need to understand, but not that formula. That's not really something that we need to know. And these go back to the independent mutually exclusive definitions on the previous page. So what I'd like to do is pause the video for a moment, go over and get the practice section, which looks like this. All you have to do is ask me for it and I will give it to you. But look for the practice section for conditional probability and multiplication rule so we can go through some problems. Hopefully you've taken a minute to do this. So read through the problem. There are 25 students, 15 are male, 10 are male. Needs to have 2 kids move a table and randomly select 2 students from a class. What's the probability that both these selects are boys? So pause the video, take a minute, see what you think the problem is before I put this down. Hopefully this is where you ended up. 10 out of 15 times 9 out of 14. Where did this come from? Well, 10 out of 15, or sorry, excuse me. Let's fix this real quick. Hopefully you did not get this. The correct answer should be 10 out of 25. So 10 out of 25 are males. Because there's 25 kids in the class, 10 are male. Now we selected a male. What's the probability to select another male? 9 out of 24. So hopefully you didn't make the mistake that I made the first time. But this is what you should have. 10 out of 25 are male. We have a male up in front. We need to pick another one to move something. 9 out of 24 are males that are left in the class, and you can multiply those two. So if you look up here, this is a situation where they are dependent. The reason they're dependent is because this outcome was affected by this one. Take a minute to look at this problem and see what you can come up for this problem with solving it. Make sure you pause the video here for a second and do the work, and then I'll unpause. All right, I hid this because I want you to think about this, and I want to make sure that the answer just doesn't pop up. So you have 3 true-false problems. First thing you have to understand is that your ability to get the first one, second one, third one right does not change depending on if you got the previous one right, which means they're all independent. So all these are independent guesses. So we can just multiply the probabilities. So that is this is the probability that you get the first one right, second one right, third one right. They're true false problems. You got a 1 in 2 chance, or 1 out of 2 chance of getting them right. What's the chance you can guess on a multiple choice and get it correct? 1 out of 4. So this is the probability here that you would get all 5 correct. So this is the first 3 problems. You have a 1 in or 50% chance, or 1/2 chance of getting them right, and a 1/4 chance of getting multiple choice problems right. Now, this is a graphing situation. So what's the probabilities here? Take a minute, pause the video, see if you can come up with the same answers that I did. All right, so this problem is based off of a graph. So we're not going to be doing, the numbers in the problem. You're going to have to use a graph to get the problem. So what's the probability if 2 different pedestrian deaths are randomly selected? What's the probability that both are intoxicated? So what's the probability that the first one and the second one's intoxicated? So this is going to be a multiplication situation. So here we go. I put here DI and PI for driver intoxicated, pedestrian intoxicated, and a little and symbol. Sorry, it's messy. But 59 out of 985 times. So really what we're looking at, we're looking at this right here. So this is both, this one is yes, and this one is yes. And if you kind of think about it this way, this is the one where it intersects. That's the 59 out of 985. And let's assume that we're, out of 985 people, we already asked one, we only have 984 more to go, and 58 out of them will also say yes. So this one down here, given the fact that the pedestrian was intoxicated, and I want to stop here for this part here. So given this, anytime we're using the word given, we're going to use this vertical line. It's going to go back to that situation where this, given this, occurred. So given the fact that the pedestrian was intoxicated, what that means is we are only looking at the situation here where the pedestrian is intoxicated. We are only looking at this situation. So we're only looking at this group of 325 people. And of that 329 people, 59 of them, or 325 people, 59 of them, the driver was intoxicated. So that would be the answer to this one. The last one that we're looking for, that neither driver nor pedestrian were intoxicated, is we're going to go back to here. We're looking at neither one. So we're looking at no and no. So this one is here. So this one, I made a slight mistake. This one should be 581, 580, and 579. So it should be 581 out of 985, which is neither one was intoxicated when they got in the accident. Then again, 84, 83, because they are dependent. We're going to ask, 3 different people out of a group of 985, and what is the result? Hopefully this helps.